Hello again, and welcome back to section 8.2. In this section, we are going to be actually completing a hypothesis test. We have, for the first time, we have laid all the groundwork that we need with section 8.1 for us now to complete a hypothesis test from start to finish. So in section 8.2, we're going to be doing the first type of hypothesis testing, which is doing a z-test for the mean. Just like in section 7, or chapter 7, we are going to have 3 different types of hypothesis testing. We're going to be doing a test for the mean where we have this population standard deviation. We're going to be doing a test for the mean where we don't have the population standard deviation. And then we're going to be doing means for proportions. So our first type here is a z-test for a mean, which means the sigma is known. Okay, we know the population standard deviation. Now remember though, in real life, oftentimes researchers don't know the population standard deviation. If it's been studied extensively and there's lots of information, they may have a very good idea what the population standard deviation is, but the only way to really know the population standard deviation is if you were to take information from the entire population, which is very difficult in a lot of situations. Most populations are too big. So we're doing this first because it's a little bit easier, even though it's not as realistic, but it's a little bit easier. And then in section 8.3, we will do a test for the mean where we don't know the population standard deviation. I missed a word here. I said population deviation instead of standard deviation. Okay, so right now we're going to be working as if we know the population standard deviation. Now this should be a very familiar pattern. I know we've seen this, I changed colors, but it's really the same flowchart that we've seen several times. So now we're doing hypothesis testing instead of confidence intervals, but the decision making is exactly the same. Before we start the hypothesis test, we need to know, are we doing a hypothesis test for a mean or for a proportion? So for this section, we're going to be doing hypothesis test for the mean. Once we decide we're doing a hypothesis test for the mean, we have to know, is the sigma known, the population standard deviation known, or do we only have the S? Do we only have the sample standard deviation? In this case, for this section, we are going to know the sigma. We're going to know the population standard deviation, which means then we're going to go ahead and use Z off of the chart, off of our table. We can do what's called a Z-test. So we're going to be doing a Z-test, hypothesis test on the mean. So this will be for section 8.2. When we get to section 8.3, we'll only have the S. And so because we only have the S, we'll use a T. And when you use T, that means you're doing the degrees of freedom and you're stopping partway down your table and not going all the way to the bottom. And then when we get to 8.4, we'll be working with proportions. And when we're working with proportions, again, doesn't matter what the standard deviation when we're working with proportions. That doesn't come into play with proportions, so we can go back to using Z again. All right, so let's get started. As a reminder, we said this at the end of the last video, but go through it again. Step 1 is to state the hypothesis and identify the claim. So step 1 is the hypothesis statement. Step 2, we're going to find the critical values. This is from the chart. Step 3, we're going to compute the Z value or the test value. This is a formula. Step 4, we're going to make a decision to reject or not reject. And then step 5, we're going to have a conclusion or a summary. And I mentioned in the last video that our formula was going to look very familiar. We used this in chapter 6 when we were doing the central limit theorem, and which makes sense because remember the central limit theorem we used when we were comparing or finding the probability of a sample having a certain mean or proportion, and when we're doing hypothesis testing we're working with samples. So it would make sense that we need this formula that has the square root of n on the bottom. The more simplistic z formula doesn't have the n on the bottom because we're just looking at a individual. So that one has x minus mu over sigma. But in this case, we have an average of x for the mean sample mean. And then we have to adjust our z-score based on the size of the sample. And then to review again from the last section, if we are in the critical region, we do reject, and there is enough evidence to support the claim made by the alternative hypothesis. You may have heard this in some situations referred to as having a statistically significant difference. If you've ever heard that term, statistically significant, that means there was enough evidence to reject a null hypothesis, and they use that terminology of statistically significant to indicate that. Now, if the z-value is not in the critical region, we don't reject, and there is not enough evidence. So, in summary, if it is in the critical region, we do reject, and there, let me add to that, we do reject, and there is enough evidence to support. If is not in, our test value is not in the critical region, we do not reject, and there is not enough evidence to support the claim. Okay, so it's always, again, always either all in the positive, is, do, is, or is not, do not, is not. It's either all in the negative or all in the positive for the ones that we're doing. Again, that changes when we allow the claim to be on the null hypothesis. But we're not going to do any problems like that. With all our problems that I'm going to present to you in your homework and in your examples here, we're going to have the null hypothesis be not the claim and the alternative hypothesis be the claim. If we put the claim on the null hypothesis, on the first hypothesis, that messes this up. It really kind of messes everything up. That's why I don't want to present them to you like that. I want to show you the way that's considered best practice and just stick with that. Also, remember, there's actually 3 types of ways to do a hypothesis test. There's the traditional method that we're doing. So that's right here what we're doing, the traditional method. And there is the p-value method, which is pretty common. And then you can also do hypothesis testing using confidence intervals. So these are 3 different methods, but we're not going to do the p-value or the confidence interval method. We're going to just stick with one, again, hopefully so that you really understand the concepts of what we're doing, stick with the same method, and get comfortable with that. If you ever in the future take another statistics class or use a hypothesis test for some sort of research that you're involved in, you will be able to pick up the p-value method or the confidence interval method very easily. If you understand what a hypothesis test is, all it is just computing a different value and comparing it a little differently. They're not that much different that if you need to learn them in the future, if you really understand what we're doing now, you'll be able to pick them up very easily. All right, so just a little diagram, little images here to help us understand the reject or the not reject. So if you remember from section 1, if we had this type of a statement, okay, and this number after this could be anything, you know, let's say the null hypothesis is that mu is 50, and then our alternative hypothesis is that mu is less than 50. When we do our second step for our critical region, we would have drawn this type of a shape with the left side shaded. If that's the case, then that red shaded region, that region that's below the critical region, or the critical value, giving us the critical region, if we're in that red area, we're going to reject the null hypothesis. For a right-tailed test, again, this could be anything. Say this is 42, greater than or equal to 42. If we have a greater than sign, that means we're looking at the right tail of the normal curve, and we're going to reject the null hypothesis if we're in that red shaded area to the right of our critical value. So our critical value would be here, and we would reject anything larger than that critical value. And then I didn't mention it here, but if it's not in there, if we're in this clear area, we're going to not reject, fail to reject, not reject. Okay. And then with a two-tail, that's when we have the not equals. So say this is, 4.8. Not equal to 4.8. Then when we do our critical values here, if we're below the negative critical value, we reject. If we're above that positive critical value, we would not reject, or we would reject. And then if we're in between them, we would fail to reject. So with the two-tailed, you would reject if you're down in the lower or the upper. And that's a two-tail. So here we go. Here's our first full hypothesis test. So a researcher in this case believes that the average number of hours a person in their state spends in traffic each year is more than the national average of 46 hours. So remember, you could be comparing information from now to a study from the past. You could be comparing a sample that has had a treatment done to it, such as medication, or in the last section we talked about adding insulation. We talked about putting an additive in a battery to try to lower, the insulation was to lower the costs of heating, the additive to the battery was to raise the life of the battery. Those were treatments. In this case, we have a subset of a larger set. So there's a national average, and they wonder, the reason they're doing their test is because there's the national average, and they're wondering if their subset of their specific state matches the national average. Does it have the same average number of hours as the national average, or in this case, they think that it is more. So we're going to start with our hypothesis statement. We have always our null hypothesis and our alternative hypothesis, and then we put these colons to say that's going to follow. Our null hypothesis is always our status quo. So it says, assume the population standard deviation is 3.6. We'll come back to that. The national average, here we go, I missed it. The national average is 46 hours. So the status quo is the national average that's been studied in the past, and it's 46. And then he thinks that his state might be more. So he's going to run a hypothesis test on that claim. So I'm not going to write this every time, but remember, we're always going to have the first one as the not the claim, and this is the claim. All right. So step 2, we need to find our critical value. So this is our hypothesis statement. Step 2, we need to find our critical values. Value or values. So in this case, do we have one critical value or two critical values? Well, we're going to just have one. Remember, whether it's left tail, right tail, or two tail is based on whether we did less than, greater than, or not equals. So in this case, because we have a greater than, this is a one tail right, or just right tail test. We only are concerned about greater than. Our picture is going to look like this. Ooh, not like that. That looks horrible. It's a little bit better. Okay, so we're only looking to the right side of our normal curve. And we're doing a z-test. How do we know we're doing a z-test? Well, we know we're doing a z-test because up here it says the population standard deviation is 3.6 hours. And if we know the population standard deviation, that's our sigma. And if we have sigma, we do a z-test. Then it says a random sample of 30 subjects is selected. We'll get to that in a minute. Test the claim at alpha 0.05. So to get the critical value, we need to know that alpha is 0.05. We have to know we're doing a z-test, and we have to know it's right-tailed. So our picture's all set up. We know what we need off of the chart. We need right tail, z-value, alpha 0.05. So let's pull up our chart. So right tail, which would be a one tail on our chart, 0.05, and we're going to get a z-value, which is all the way at the bottom. So we're going to go all the way to the bottom of our chart until we get to that very last row, which is our zero, not zero, zero. And that is 1.65. So we're doing a z-test. Z's are at the bottom, 1.65. So this number right here is 1.65. That's our critical value, making our critical region up above 1.65 and our non-critical region below that in the non-shaded area. So this area that's shaded, that is the critical region. Okay, so now we're going to compute our test value. Our test value, we're going to use our formula, x bar minus mu all over sigma over, I'm going to write it like this because it really should be more underneath like that to alleviate confusion. X bar in this case, that's our sample average, 47.8. Our mu, we already listed. That was what we used in our hypothesis statement. 46. Mu equals 46 is what we used in our hypothesis statement. Our sigma, we said, was 3.6 hours. 3.6 over our sample size, which the sample size was 30 subjects. So we get all those filled in. And remember, this formula is not going to be very useful to you if you can't remember what an x bar is or what a sigma is. You have to know those variables. Please study those if you're having problems with those. I have announcement from a few weeks ago where I gave you a link to a Quizlet that you can use to study, or you can make your own cards, but please know what all the variables are. All right, 4.7 minus 46 would be 1.8. And then we're going to divide by whatever the answer to the bottom is. So this is how I like to do it on the calculator. Okay, so we already have the top computed. I'm going to compute the bottom. Okay, so the bottom is 3.6 divided by square root of 30. And I'm not sure why I put a square root on the bottom here. It should just be answer, not square root of the answer. Okay, so now we're going to do 1.8 divided by answer. And that gets us 2.74. Now that is our test value. So step 3 is test value. We get the test value from the formula. So we have hypothesis statement, critical values, test value. What do we do with our test value? Well, we take our test value and we see where it falls in comparison to our critical value in our critical region. Well, if we go up here, we can see that 2.74 is going to fall up above 1.65, which means it's in the critical region. So we're in this shaded area. I always joke with students, think of it as, you know, if you're in the dark cave, if you're walking along and you end up walking into that dark area, into that cave, then you're going to reject. We don't want to be in the dark area. Doesn't necessarily mean it's bad to reject, but to help you remember it, we reject being in the dark cave. So here's a picture of that same thing on this slide. So we're in this critical region, okay? So because we are in the critical region, we are going to reject. We is in the critical region, so we do reject. And then the conclusion is that there is enough evidence to support the claim that the average amount of time a person spends in traffic each year in the researcher's state is greater than 46 hours. Now let me show something really quick about how you'll see these on the exams. So on the exam, for step 1, you'll see 1 and hypothesis test. It will actually say that. It'll say 1 hypothesis test. Then it'll say 2 critical value or critical region. I can't remember which it says. Okay, so it'll say critical region or critical values. Then for part 3, it'll say test value. Then for step 4, it will say decision. And not only will it say decision, but it will have everything filled out except for the do, reject, and the is in the critical region. So the only parts that you'll have to fill in, I put them in the bold here. So the only parts that you conceivably would have to fill in is do, reject, and is in the critical region. So we blank the null hypothesis because the test value blank. So you have to fill in this blank that will be on the exam and this blank that will be in the exam. Okay. Same thing with the conclusion. There's going to be a blank here, and that's all that you'll have to fill in. You don't have to write the whole sentence out. You just have to fill in the blank with is or is not. There is enough evidence, there is not enough evidence. So remember, in this case, because it was in the critical region, we do reject, and there is enough evidence. Those are the only parts that you're going to have to fill in on the decision and the conclusion. The rest of it will be filled in. So the kind of the basis will be filled in, and you just have to fill in what your decision and your conclusion is. Okay, so we did reject the null hypothesis, meaning we're rejecting, we found this null hypothesis guilty for that specific state. So this null hypothesis is guilty. We're saying, no, it's not 46. It's greater, that we believe it's greater than 46. We're going to reject that and say we have enough evidence for the charges or the claim that the mean for their state is bigger than 46. And that's it. That's an entire hypothesis test. I know it seemed like it was so much when we were leading up to it. There's a lot to kind of build up to it, but once you get to it, they're not terrible. We just have to remember to take it step by step and do each of those steps in order and carefully and compare our numbers correctly. All right, so let's look at our second example. 1 year, the average score on the SAT math test was 515. Okay, so this is going to be our null hypothesis. That's our status quo. So the status quo is that the mean is 515, assuming that means the national average. The SAT is normally distributed with a population standard deviation of 100. So we have the population standard deviation, which is our sigma. That means when we get to step 2, we know we're doing a z-test. When we get to getting our critical value, after we do our hypothesis statement, when we get our critical value, we're going to need to know that's a z-test, and that's exactly because we have a sigma. Remember, if we don't have sigma, if we only have the sample standard deviation, we have to use a t-test. A local high school randomly selects 36 students because they fear their students are testing below average. Below average. That's our null hypothesis, that this group, this high school, is performing below the average of 515. The mean of their scores was 509. We don't need that quite yet. Is there enough evidence to support the claim that the students did worse than average at alpha is 0.10? All right, so we know it's a z-test. We know our alpha is 0.10. What's the other thing that we need to know? Well, we need to know what tail it has. It's less than, so our tail is to the left only. Only concerned if they're scoring under the average. So we're doing a left tail, one tail left, z-test, alpha 0.10. So if we go to our chart, we need a one tail, .10. I think it was 0.10. Let me double check. Yes, 0.10. And we're doing a z-test, so we're going all the way down to the bottom. Which is the 1.28 value that we got before. Okay, so we're using 1.28 again. In this case, it's negative 1.28 because it's to the left. So if we get below negative 1.28, we're going to reject, and if we're above that, we're going to not reject. So if we're in this shaded area, we're going to reject. That's the rejection region. I'm going to erase that because I don't want to be confused if we end up not rejecting on this particular problem. So, but that's the rejection region. Now for step 3, we're going to use our formula. We're going to do our test value. And that is z equals x bar minus mu over sigma over square root of n. Our x bar is our sample average. That was 509. The mean of their scores was 509. The population mean was 15. The sigma is the 100. And then the square root of n, there was 36 in the sample. So 36 in the sample, and our sigma was 100. Again, I'm going to do the top because it's usually pretty easy to compute. That's a negative 6. And then I'm going to divide that by whatever answer I get for the other part, for the 100 over. Okay, so we have 100 divided by square root of 36. Yes, you could type in 6 if you already know square root of 36 is 6. So we have 16.6 repeating, and we're going to divide the top number by that. So negative 6 divided by that answer gives us negative 0.36. Okay, and what do we do with that? Well, that value is only about right here in comparison to our 1.28. It's not anywhere near low enough to be below that. We're only going to reject if we get below. So if we had, like, say, negative 2.5 or negative 1.7, then we would reject because we'd be below negative 1.2. Don't forget, this is 0. And so this is like a number line to the left going this way, number line to the right going this way. So negative 0.36 is not as negative as negative 1.28. So we're not down far enough to be in the rejection region. So what does that mean? Well, since we are not in the rejection region, since our 0.36 is up here, not low enough to be in the negative 1.8, we do not reject the null hypothesis because it is not in the critical region, the test value. And so our conclusion is there is not enough evidence to support the claim that the students at their school test below average. This is one of the things that's always very frustrating when I see data from schools and such. You know, people collect data from schools and they'll take something like this and they'll say, oh my gosh, you know, this student is performing below average because we took a sample and the average scores of those students was 509, and that's, you know, 6 points below the national average. But with that small of a sample and that small of a difference, that is not statistically significant enough to say that the students are actually testing below average. It's just the difference between a sample and the population. A sample can vary slightly. And in this case, by having a negative 0.36 Z for our test score, that means, yeah, it was slightly below the average, but not so much that it's unexpected from a sample. Only negative 0.36 standard deviations below the average. That's not much for this situation. So not enough evidence to support that. So they took that null hypothesis to court, said, we don't think our school's equal to 515. We think we're going to charge it with being below 515, but the charges didn't stick. There wasn't enough evidence to support that claim. Okay, so now on to, I think this is our last. Yes, this is our third and last example from this section. So a report states that adults skip breakfast an average 50 times per year. Researcher wants to see if adult college students skip breakfast at a different average. So here again we're having all three of these examples were subsets. So there was, where all of our other examples I think were all treatments. These are all subsets. So we've got, we had the national and the state, and in this case it was the national and the school was a subset of the national. And then in this case we've got the national average of all adults, and we're looking at a subset of adult college students. Our hypothesis statement, we're going to start with what is the status quo. Where are we starting at? What's the origin? Well, the origin is a report states adults skip breakfast 50 times per year. That's our average. Status quo average. Adults skip at an average of 50 times per year. Do we want to do our mean with a less than, a greater than, or a not equals? Well, if you read what the researcher is wanting, it says a researcher wants to see if adult college students skip breakfast at a different average. Doesn't specify higher or lower. They just want to know if it's different, if it's not equal to 50. They're not specifying whether they think it's higher or lower. They just think it might be different. Second step after our hypothesis test, or hypothesis statement rather, is to do our critical values. Now for our critical values, we need to know the tails, so we know which row to go to in the chart. We have to know whether we are going to the one tail or the two tail. So we need to know if it's one tail or two tails. And we're going to have to know the alpha, and we're going to have to know whether it's a T or a Z. So our alpha in this case is 1%, so 0.01. They did it as a percent this time, but we know that's the same as 0.01. In this case, it's a two-tail because it's not equals. So we're interested in knowing if it went up or down. Okay, so we want to know about this tail and this tail. And then we need to know that it is a z-test, and the reason we know it's a z-test is because it's from section 8.2, but when you're looking at problems where they're mixed up, it says assume the population standard deviation. They're always going to give you a standard deviation. It's whether it's the population standard deviation or the sample standard deviation. In this case, it's the population, so that's our sigma. Our sigma is 3.1, which means we can use a z-test. So we're going to go to our chart, alpha 0.01, two-tail z-test. Alpha 0.01, two-tail 0.01 z-test. Oh, that's the same value we got just a bit ago at the end of section 8.1. That's the 2.58. So we're going all the way down to the z-value, and that's 2.58 if we are at two tails, alpha 0.01. So 2.58 if we round to what Alex likes us to do. And then if this is 2.58, this is always symmetric, so this is negative 2.58. And we're going to reject if we're below negative 2.58 or above 2.58. So let's do our test value. Z is x bar minus mu over sigma over square root of n. X bar is from the sample. Their sample was 51.2 times per year. Mean is the mu, that's the 50 that we had up here. So the mu in the formula is the same as the mu from our hypothesis statement. Our sigma is that 3.1. And our square root of n is the sample size. 40 adult college students was our sample size. So square root of 40. That gives us 1.2 for our top number. And then I'm going to divide that by whatever answer I get off the calculator for that bottom part. So I've got 3.1 divided by square root of 40, and then I'm going to take 1.2 divided by the answer. You can do it all the way through. If you have a different way you like to get that into your calculator, as long as you're getting the answers right, do it the way that you're comfortable with. So 2.45 is what we get. And oh, that's close, but not quite. So when we compare this, 2.45 would be slightly below the 2.58. Not above it though, it's not in the critical region, it's not in this shaded area, okay? not in the shaded area. And so because it's not in the shaded area, because it's in the clear area, we're going to not reject. So here's our photo, or here's our picture. 2.45 would be a little below 2.58. So we do not reject the null hypothesis because it is not in the critical region. There is not enough evidence to support the claim that the average number of times adult college students skip breakfast is different from 50. So we did not come up with enough evidence to convict the null hypothesis. So we have to say, oh, the null hypothesis is correct for this group of people, the same as it was for the national average. Okay, so I'm going to stop here for this video. And so now you should be, fully capable and able to do your homework for section 8.2. And we will come back and I will do 8.3 and 8.4 in the next video. But you've now seen 3 hypothesis tests for a z-test for the mean when we have the standard deviation of the population. Go back to our flow chart here. We knew on all these problems we were doing a mean and we knew the standard deviation. So we were doing z. So for all of these it was mean with the standard deviation known, so we used z. So when we come back for section 8.3, we'll see examples of where we have to use the t-test because we only have the sample standard deviation, and then we'll do section 8.4 where we are going to do proportion z-tests.